Hello, good evening, and welcome to NARC Live on Wednesday, the 20th of October 2021, coming to you live from Norfolk on the east coast of England with Tammy M0TC.
Hello.
And me, David G70RP. Great to see you. On tonight's show, Alan Wolke W2AEW shows us how to put a multimeter and oscilloscope to great use in the shack. We've got some wonderful pictures from TED G4OZG. And we find out what on earth this is. I must say we've had quite a few entries this week, just to say it's a that's an understatement probably, but if you haven't entered and you want to pop it onto Facebook on BATC, then we'll read that out in the end as well when we come back to that part. But first, Donard M0KRM sent us this picture of a brand new radio that's coming very soon. You may have heard about it. I've seen it on a couple of things now. It's called the Zygo X6100. It's, in their words, a revolutionary self-contained 10 watt HF and 6 meter SDR transceiver with a large colour display, automatic antenna tuner, and a built-in high-capacity battery. It's an ultra-portable SDR, basically. And I guess one of the key things is about it, the price, which in euros, which is the only price they've published, is €695. So I guess hopefully might make it over here for about £600. It's going to be launched on 15th of November. But there's some nice close-up pictures there. Thank you very much for Donald showing us that. And I guess they're going to be treading on some toes, maybe the 705, the IC705 recently launched, a very portable transceiver, although it does a bit more maybe with the digital side, possibly even I'm trying to think of the KX3, the KX2, not my KX, is it KX? Yeah, I think it's that. Anyway, you know, this Vellicraft, the very, very ultra portable radios. So have a look out for that anyway. I'm sure it will appear in Radcom and Practical Wireless and online details of it soon, but that looks something exciting for about £600 or so. Thanks for sending it to us, Donald. Now, Bob G6PWS sent us some pictures from around his village. Firstly, the 2 frogs in our pond were croaking away like mad before he found them and took... This picture's rather nice, isn't it?
Yeah. Yeah. Funny looking things.
That does look rather, just peeping out from underneath the rock as they do. And this one, the robin, was singing away, even when he got up close to it with the camera. And a lovely sunset, and found the ladybird in the middle of the flower. You just see that there, look at that last flower on the bush. Beautiful.
Really good.
Thank you very much, Bob. That's all it takes, you know. Keep in touch with us, send us pictures, stories, anything that you come across in the week that you think your fellow NARC members might be interested in. Please keep in touch with us. Now, someone else who sent us some pictures this week is Ted G4OZG. He sent us loads of really good pictures, but I've picked these first 4 and we'll share some of the others with you later on. Let's have a look at these if we can, Tammy. Now this, he probably didn't, well, he didn't know that I'd been there as well. This is Mount Washington, or it's taken on Mount Washington. If you just look in the bottom of your screen there, you can just see I think it's a train.
A train.
And it's called the Cog Railway, and it is something I went on myself. It's in Mount Washington, which is the place I went to was Nashua, which is very near there. New England. I'm trying to think of New Hampshire. I think it's New Hampshire, I believe. State. Well, our guest shortly will
is nodding,
confirm.
so.
Our guest is nodding. All right, so we've got it right. But have a closer look at this one. So this was. I must just read the words that Ted kindly wrote about this. So my wife Margie and I did a leaf peepers trip around New England in October 1990, and also went to the summit of Mount Washington, not by the Cog Railway though, as it was too slippery to drive ourselves up. So it was by 4-wheel drive, low-geared minibus. Terrific views of the train coming up. This next picture, and this is the bit that when I saw that, I knew exactly what that was, because look at the logo, how distinctive that is, and the angle of everything. A photo of Ted with the Cog logo, very windy and cold. Then Margie retired to the cafe while I explored, and I remember going up this. Unfortunately, when I did it though, it was very, very misty, and it was I couldn't see any views or anything from the top. But it was fascinating to go on this train that obviously, as you can see, travels at that sort of angle all the way up Mount Washington. And that's why they built the boiler and everything else on the level, but the rest of it, the cab and things, is all going up. It looks really weird when you see it in real life, but anyway, Ted, thank you for sharing that. This shows you how cold it really was, because he said the summit's at 6,200 feet, lots of ice on everything. Note the chains holding the building in place. Wow. My goodness me. The highest wind speed recorded here was a gust of, now get this, 231 miles an hour.
Wow.
Can you imagine wind being that fast? Something to do with a Venturi effect caused by the terrain. It was supposedly 50 miles an hour when we were there, so that would have felt 50. It's pretty steep, isn't it?
More than we get here, isn't it?
That's all on Mount Washington. And finally, this picture, lot of aerials with ice, he says. I'm not surprised. And you can just see the ice is sort of moving to the right. Look, if you look at it closely, it's sort of obviously that's where the wind was going, I guess, when the snow hit. Anyway, Thank you very much, Ted, for sharing those. We've got some more photos, and might be trains amongst the other pictures. It's not me. I know I would show trains at every possibility. That'd be my other hobby, but this is other people sitting in. If you've got some news for us, though, or pictures or anything else, please let us have them to this usual address, radio@dcpmicro.com, at the bottom of your screens now. Let us have that by 3 o'clock on a Wednesday, and we'll feature it either on that night show or one very soon afterwards. Now it's that time where we go to Tammy and say, let's have a look at your little people, please.
The little people. Here's the little people for this week.
Oh, I love it.
Do you know what the date is?
No.
Well, tomorrow is the 21st of October, which is the day that they went back to. Although it's not obviously 2021, but it was 21st of October.
Do you think for those people who have not seen the film and not reading it, we ought to explain what this is, though? So the car is a DeLorean. Yep. Very, very, very popular with me. I'm a real fan of that car. And it's called, sorry, the film series was called Back to the Future. So I guess the little character there is
Marty.
Michael Fox. Yeah, Marty, or Michael J. Fox played the character, didn't he? And but anyway, as usual, these miniature-calendar.com images, it's the imagination and the sort of skidding wheels where this car was probably about to go 88 miles an hour to go into the future or into the past. And they've just used the sort of, I guess that's sort of oil colour. Oil paint, I guess?
Yeah.
Something like that. Yeah. Brilliant. Thank you, Tammy. Miniature-calendar.com if you like that picture and want to see lots more. Every day there's a new picture. And I didn't know it was tomorrow. Yep. The date they went back to in the film.
Well, it's not the year, but it was the 21st of October was the date they went back to. So.
Right.
Yeah, there you
Didn't
go.
know that. Thank you for sharing that. So, as I said, keep in touch with what you've been doing. We'd love to hear your stories, to keep everybody in touch. And we have this competition running every week where we say, what on earth is this? And last week we asked you, what on earth is this? Okay. Yeah, we better not say what it is yet, do we?
No,
we better read
we've
out
had
some of the questions.
We've had one comment
Have
online.
we? Okay.
Yeah, which was from John, G8VPE. I think this is a device for tightening cable ties.
Okay.
He thinks.
Right. It's a sort of gun-shaped thing, isn't it? Any others on Facebook or anything? No? Okay, that's fine.
Not at the moment, I don't think.
Let's go through it. Take a big deep breath, Tammy. Here we go. Steve, G3VA. It's a zip tie gun or cable tie gun here in the UK.
Oh, you want me to read the next one?
You don't have to if you don't like. You don't get paid anymore, but it's up to you.
You read the first few.
Okay.
Just got to do something.
Kev M0KKM says the latest object is a tie wrap tool. They were supposed to tighten and cut tie wraps neat and tidy, but are useless in confined spaces. Martin G3ZQU explains, I know this one. This week's item is a zip tie tensioner and cutter offer. Mark M0YCT says, I think this latest picture is of a gas lighter for ignition of a gas hob or such like things. Thanks for the lovely work you do for amateur radio with your wife. Thank you very much, Mark, for that. Bob GSTU says, I think this is a cable tie lightener and cutter. Ricardo de Ponza says, hi guys, I reckon that mystery object is a cable strap gun. I still have mine from the days when I worked for BT. Keep up the good work. Scott M0BLH says, I'm guessing it's a tie wrap gun. I have one myself as I use it to fit tie wraps on my diving rebreather. It helps ensure that the tie wrap is tightened correctly. Mike GAEY says, this week's What on earth is it? Is a cable tie tensioner and cutter for cable ties. I think we're getting a bit of a theme here.
We are.
James M0 UKS, though, thinks it's actually a cable stripper. Mark Ribbons thinks it's a cable tie tool. Mervyn MI0 TMW says this is a tie wrap gun to tighten the tail and cut it off. Tom Miller, now he's given us a number of options. He's really covering options. Do you want to read these ones, Tammy?
Yep. One, a gun popular in the 1970s to surreptitiously fire elastic bands in an office environment. I had one of those. A spark generator to ignite acetylene for a welding torch. The inserter for a price tag holder found in the clothes when shopping. Oh yeah, I've seen those.
Yeah, that's a good idea, yeah.
A wire wrap tool used on telephone exchange type equipment where the tool wraps wire around a thin post.
Yeah, I can see that as well. Okay. Paul G4ZBA, I think it's a tool for pulling up cable ties. And if it's the same as mine, you turn it through 90 degrees when it's tight and they're cut off. Colin M0GMK says this week's tool is a cable tie gun used for tightening cable ties and cutting off the tails. There's quite a few of the same one along here. So we're nearly getting to the end now, but we want to give everybody a name check who entered, and then we will tell you, and maybe even show you what it is.
We've got Paul Brooks, who thinks it's a stapler.
Okay, yeah, I can see how that looks a bit like a stapler, the top bit. Okay, we'll count your entry there. Andy M0JGK says this item in the photo is used to tighten tie wraps. I used to use something similar years ago. And then he says, excuse me, do I win a prize? There's an easy answer to that. No, sorry about that. It's just for fun. Pete G0FVG says it's for cable ties. Rodney G0CBO says my guess this week is maybe a tool for tensioning cable ties around bunches of cables, and the trigger is used to cut surplus length on cable ties once tension is applied. And finally, Tammy, you reveal the last entry we've had.
Simon M0SIH, the item shown on What on Earth is This is a cable tie gun. It is used to tighten cable ties on cables.
So,
what do you reckon it is?
I don't know. Can we come back to us though? Because I happen to have one of these as well. It isn't quite the same one as the one on there.
No.
Okay, and if I did this, given the current trend for a certain film out there at the moment, and said this, and I said something like this to you. I'm James Bond, remember?
Oh, you're
okay,
Bond.
I'm Bond,
oh,
yeah.
Okay.
Do you expect me to talk?
No, Mr. Palmer, I expect you to tie.
To tie? You get, see? Have you seen the film? If you know what? No. Anyway, we're going to show you what it is. Our guest's groaning. I think he's going to go in a minute. Let's have a quick look at how it is. If you don't know what this is, never seen one before.
I think most people did know what it was.
They did. I think that was the general idea. And by the way, we must thank Bob G6PWS for giving us that. Yeah. But we've got a close-up camera here just to give you a very quick idea and a demo. And this is probably where it all goes wrong, doing something live. So Tammy, can we see this camera? And we haven't really rehearsed this properly. So a couple of cables, want to keep them together. And I'm sure we've all used cable ties. There can't be a radio amateur out there who hasn't used one. But normally you'd do that and you'd pull it up yourself, wouldn't you? Okay. But this little gun here, would be the case. The camera's the wrong side of us here. How can I do this? I'll show you if I show you close up.
I could hold it.
Can you? Oh yeah, okay.
And shoot it. Where is it?
All right. Oh yeah, okay. This is going to be even harder to do the wrong way around. So what it is, this thing here, and Tammy's got a finger on the gun. You put this in here, and then you pull the gun, and tight.
Oh, look at that!
And what it did, it tightened it up, and gave the right tension on it, and also cut the cable tie off and landed on our computer at the other end of the room. So really useful tool. About 15 quid nowadays, something like that. Really useful tool. It is a cable tie tensioner. So thanks again to Bob for sending us that in. Sorry about the terrible joke.
Move on quickly.
I think we ought to.
Right, this week's mystery object is, what on earth is this?
Now, can you guess what this is? All right, it's a real picture. What is this, and what is this for, I guess you could say? What do you think that is? It's real. This isn't staged for this competition. It's from one of our members. Have a look at that. We'll be putting it on Facebook and on our newsletter and on the and on the website as usual, of course. And you've got until next Wednesday at 3 o'clock to tell us what you think that is or what it's used for. Have a think.
Yep.
close look. But we'll be putting it, as I said, on the website. You better look at it anytime and on our Facebook page as well. Send your answers to radio@dcpmicro.com by 3 o'clock next Wednesday, please. Right, we're nearly on to tonight's main event. Before we move to that, just to let you know what's happening in our club this week. On Sunday at 7 o'clock, we've got the GB2RS News on repeat of GB3MB. Monday, 25th of October, we've got a Monday Night Net on GB3MB again with Tim M1MIT. Now, we've had volunteers who've been running this for the last couple of months, really, and Tim's coordinating people. We do need people to volunteer for November. So if you ever take part in that net and you just run it for one night, it's very, very easy to do, then please contact Tim or us and we'll put you in touch. And hopefully you can help run that net on a Monday in November. At 8:30, as in every Monday, 80 metre CW net on 3.543 megahertz. And next Wednesday, the 27th of October, a friend of ours, kind of someone we've met through these COVID times in a program that we actually did for the RSGB for their convention last year in 2020. His name is Joe Chester. His call sign's M1MWD. He's a real character and it's going to be great fun. We had a rehearsal with him at 6 o'clock tonight, actually, to remind ourselves and talk about it. He's calling his talk "Having Fun with a Small Station," but knowing Joe, that's going to be...
don't give anything away.
No, I won't. All right,
it's really, he's a fun guy.
He is a very fun guy. You're in for a night of entertainment next Wednesday for NARC Live at 7:30. And all the regulars as well, and what on earth is this? And your stories, please let us have them, please, because otherwise we've got nothing to talk about for the first 5 or 10 minutes. And also this card, of course, which we're happy to send to anybody you think will be cheered by a card. We'll send it to for a birthday, anniversary. If someone's not feeling too happy at the moment, very happy to send this. Just send us their name and address and we'll add your name to ours and send it to them wherever they are in the world. Very happy to do that. Now on to tonight's main event. Now, I'm sure most of us have at least got access to a multimeter or something like that, but do we really know how to use it? What's the best practical use for it? And the other thing that a lot of amateurs probably have is an oscilloscope, but even more so, how do you best use it? What's the most practical and best way of using it, particularly in the Radio Shack? We've got just the man to tell us tonight because Alan Wolke W2AEW is here from the US live to tell us more about the practical application of these sorts of test equipment in the shack. So it's good evening to Alan.
Hey, good evening to you. And thank you again for having me here. And again, hopefully this will be a nice interesting talk for everybody.
Yeah, I mean, we're really looking forward to it, Alan, because as I said, I think lots of us have this equipment, but we're not always sure quite how. It always looks nice on the bench and smart, but we're not always sure how to use it. And so we're really looking forward to hearing from you. And just before you start your talk, just a reminder to everybody at home, of course, you're welcome to ask questions and make comments as well to Alan any time, either on BATC or Facebook, and we'll read them to Alan at the end. But now, back to you, Alan. Firstly, whereabouts are you in the States, by the way? I should have asked.
I am in the state of New Jersey, about probably 30 miles outside of New York City.
Okay. All right. Well, brilliant. Thanks for joining us tonight, and we look forward to your talk. Thank you.
Very good. Just to let you know, I've got a hard stop at, let's see, it's 10 minutes to 3 in the afternoon here. I've got a hard stop at 4:30. I don't think we'll go that long. But just to let you know, just in case we run long with questions and things like that.
Brilliant. Well, so it's over an hour and a half, isn't it?
But that's why I figured. I don't think we'll go that long, but just wanted to let you know. So
thank you very much. Yeah, sure.
It is a work day here, and I've got a meeting at 4:30.
I totally respect that. Thank you ever so much.
All right. So anyway, with that, let's get started here. Again, just some practical information about test equipment in the shack here. And, a lot of this might be review and basic for many of you, but I always find that you pick up a little bit of a tip here and there. So our agenda for this evening, we're going to talk, start off with talking about meters. I mean, everybody has meters that they use, and they may be analog volt-ohm meters, kind of like, look at the little video. You can see me and my trusty Simpson 260 here. Probably more popular over there is the AVO meter, I believe.
You can hold that up again if you like, Alan, and we'll come into a close-up review, so we'll be able to see it.
There you go. So that's the Simpson 260 here. So, but I think the AVO meter is probably more popular in the UK and in Europe. The Simpson 260 is kind of the staple of analog VOMs here. So that's what the VOM stands for, is a volt-ohm milliammeter. Also, digital multimeters, or DMMs, also very popular as well. Both have their place, and we'll talk about that. And then even bench DMMs, which are kind of like the digital, the DMMs, a bit on steroids in terms of performance and features. And then we'll talk about oscilloscopes, probably the second most popular general purpose piece of test equipment that you might have in the shack. I'm not going to talk anything about things like SWR meters or antenna analyzers, things that are more specific to us hams. These are kind of your more general purpose electronic equipment. We'll talk about the difference between analog and digital scopes and what's good and bad about each of them when it comes to doing the work that we do. And then we'll talk a little bit about just setting them up, the vertical and horizontal settings, triggering settings, some best practices when it comes to probing to get to not distort your signal too much. And then a couple of tips of how you might use a scope in the shack rather than just to collect dust like a lot of them do. So anyway, with that, let's get rolling here on talking about meters. So the analog volt-ohm milliammeter, or the VOM, generally just about all VOMs have manual range selections, meaning that you've got to tell it you're measuring DC volts, you're measuring AC volts, you're measuring current, and you have to kind of know what's the highest reading I expect to see, so that you can select the appropriate range. You have to be able to select that manual range selection. You'll notice a little bit of a theme here that you have to think when it comes to using VOMs. And in my mind, that's not a bad thing, okay? So again, the range determines which scale you're going to use. For example, if I was looking at DC volts and I move my pointer over to 3, I would use the scale here, okay, that in this case goes up to 300, so I just have to mentally move the decimal point 2 places and use that scale. Right? If I moved it up to 12, I would use the one that's labeled 12, and then the other 2 are labeled appropriately. So you do have to, the scale that you use on the meter is going to be determined by what range you set. There are generally separate DC and AC scales because the sensor circuit that is inside of the meter to convert AC into something that can be read is a little bit nonlinear. So the scale readings are a little bit off compared to using the scales for DC. So you'll notice that in this case, just the AC ampere scale is different, but the AC and DC voltage scales are the same. But again, each meter is going to be a little bit different, but just be aware of that. And the scales have got tick marks. Okay, we can break them down into major tick marks, which are the ones with the numbers labeled after them. And usually there's a sub number of ticks underneath. Usually it's divided by 10, so they make it easy. So if I can see I've got 5 volts between these 2 tick marks here, for example, on this 25 to 30 volt AC, or excuse me, this is an amp scale. But you can just take that difference divided by 10 so you know how much each of those tick marks means in terms of value. Again, makes you think, which isn't a bad thing. You have to think a little bit about parallax error. Well, what is that? Parallax error is the fact that the meter pointer itself isn't sitting directly on the meter face. There's some distance between that, the pointer itself and the meter face. So if you're not looking directly straight on the meter, the meter reading could be off a little bit in terms of what you interpret, because the tick mark that you line up with might not be the one that is directly below the pointer. Oftentimes you will see meters with a mirrored scale. They'll have a band along the arc of the meter that is a mirror. And the intent is for you to adjust your viewing angle so that the mirrored image of the back edge of the pointer is just below the pointer itself. So you literally can't see it. And that way you know that you're looking straight dead on the face of the meter, and that therefore the tick mark that's sitting under there is the actual reading. So it avoids you from having this parallax error of seeing, of maybe interpreting the incorrect tick mark. But that's why you have the mirrored scale, is to avoid that parallax error. So many VOMs will also have special connections. If you look at this old Simpson 260, there's a number of different connections here, common and plus, and then output and things like that. So some of those special connections are associated with specific ranges or functions. Okay, so you have to become familiar a little bit with which connections you need to make, you know, for a given measurement or a measurement in a given range. Generally, these separate connections are going to be for higher voltage ranges and higher current ranges, or maybe a specific voltage or current range. Now, there might be special ranges, okay? As we can see here a little bit is a 1 volt range and a 50 microamp range and things like that that aren't just selected only by the switch. Oftentimes, these meters have something called output. I wonder if anybody knows what output means, okay? Well, it's not that the meter is outputting a signal. What that is, it's a special AC coupled input when you're measuring an AC signal that might be riding on top of a DC bias. So what it effectively does is it puts a capacitor in series between that junction and the AC voltage measurement range within the meter. Where this is useful oftentimes is if you're looking at a valve or tube audio amplifier, for example. The output stage is often coupled into an output transformer. And if you wanted to measure just the audio voltage, the AC voltage on the primary of that transformer, you don't necessarily want to see the plate voltage that's on the valve or the tube. So using the output function would allow you to essentially use a series coupling capacitor to remove the DC bias. So you only measure the AC content that is riding on top of that DC bias. So just one example of, you know, one of the special functions that you'll find oftentimes on a VOM. So, and here's how you kind of use some of those. For example, let's say I wanted to measure current using the 10 amp range, okay? So if we look over on my meter face here, I would want to select, in this case, this position here. In the case of the Simpson 260, the small letters, the subscript letters, if you will, are generally the special ranges. So in this case, this same switch position is used for 10 milliamps with the normal connections, but then it's used for 10 amps as well if you use these two connections to stick this meter in series to measure up to 10 amps. Okay. So let's say I want to measure on the 1 volt range. Okay. You'll notice that this switch position here is normally for the 2.5 volt position if I use the normal common, you know, plus and minus common connections. But if in that same switch position, if I move the probe from this position to here, now we'll use the 1 volt scale. Okay, in which case, in this case, it would be this one that goes up to 10, and we'd have to move the decimal point, you know, 1 point for all the measurements across that arc. Let's say the 50 microamp range. Starting to notice a theme here. The 50 microamps, here's the 50 volt range, but it's also the 50 microamp range when I use the common and the 50 microamp jack. Okay. Same thing on the 1000 volt range. Okay, you'll notice the theme here. There's my 500 volt and 1000 volt connection, again, using the common connection here and my 1000 volt jack. So you can kind of see how all that works. Okay, so every meter is going to be a little bit different when it comes to the special jacks and how you use them. But it's just a matter of becoming familiar with, you know, what those special jacks are on your particular VOM, so you can make the most use out of it. Again, I recurring theme here again, it does require you to think a little bit about it, and that's not a bad thing. So let's talk a bit more about VOMs, and what about loading? Okay, so if we take a look on the meter face here, you see the text here says 5,000 ohms per volt AC and 20,000 ohms per volt DC. What does this mean? Well, it could mean one, you know, the meter's sensitivity. It could mean it's the input resistance of the meter. It could mean it's the meter's, it gives you an indication of the meter's full scale current rating, or it could be all of the above. And the answer really is, it's all of the above. It's all different ways of expressing that same thing. All right. So essentially what you do is you multiply the scale that you have set from when you're measuring voltage by this number to determine the resistance that the meter presents between its two leads. Okay, so for example, if you were on the 1 volt scale, the meter looks like a 20K ohm resistor. So it's something to think about, because you might, well, I want to measure, on a 1 volt scale. Think about what happens to your circuit if you connected a 20K ohm resistor to that spot that you want to measure. All right, so it is something to think about. It is a measure of the meter's sensitivity, because it really is giving an indication of the meter's full-scale current rating. So one way to think about this is the meter is 20,000 ohms per volt. That kind of means that if we take 1 volt divided by 20K, that gives you 50 microamps. That tells me that the meter is a 50 microamp full scale. That also kind of gives you an indication of the meter sensitivity. So it really is all three of these things. Now, some meters can be as low as 1,000 ohms per volt. Like in this case, you'll see there's a big difference between the DC voltage ratings and the AC voltage ratings. Some could be as low as 1,000 ohms per volt, which present a reasonably heavy load on a lot of semiconductor circuits. Okay, most what I call good VOMs are 20,000 ohms per volt or more. That's probably the most common that you'll find. So you do have to think about that when you're measuring your circuit, is what kind of a load is my meter going to present, because the meter is not completely benign. Sometimes connecting the meter up may affect the way the circuit operates because of that loading. Now, so you might say, I always want this number to be as big as possible. And in most cases, that's true, but not all cases, all right? The low values aren't always a bad thing. And so let's think about why that is. Probably the most common reason why these low values aren't necessarily a bad thing is particularly when you're measuring AC, and oftentimes when you're measuring mains voltages, maybe in your house. If you have an extremely high input impedance and you go to measure the power coming from an outlet or something in your fuse box or something like that, or breaker panel, if there's a very, very high input impedance, the wires, the probes themselves, and the wiring in the house could be acting as an antenna and essentially build up a bit of charge, just capacitively build up a charge and give you a reading on the meter that isn't really there, where if you put any kind of a load on it, that would be collapsed away. So having a lower input impedance in those instances will help to drain away those stray charges so that you can actually measure a true measure. I know here in the US and maybe in the UK as well, when doing house wiring and things like that, oftentimes the voltages are measured using something called a wiggy. And I guess it's a trade name for an instrument that's used here. But what it is, it's a voltage indicating device that is basically a low impedance solenoid. So when you touch the wires to a live circuit, the solenoid kind of vibrates. You can almost tell it's energized or not just by whether it vibrates or not. It also presents a significant enough load so that any stray voltages are collapsed down. So you truly know whether the circuit you're measuring is energized or not. So again, sometimes having a lower input impedance, particularly when measuring higher power AC, is not a bad thing. So one thing I always say about analog VOMs is you should always have at least one. Okay, the reason for that is that they're cheap. You can often get them for free because nobody wants them anymore because everybody has their fancy DMMs now. So it's always handy to have one. They're generally pretty rugged, as long as you don't abuse them too badly. They're generally pretty rugged and take some abuse. They also generally don't require any batteries. Now, I put a little asterisk here because the only time you really need batteries in any of these VOMs is if you want to use them to measure resistance. Now, a digital multimeter is probably a better tool to measure resistance anyway. So if you never need to measure resistance on any of your VOMs, just don't put the batteries in it. And that has the added benefit of you don't have to worry about any battery leakage and damage from leaking batteries from a meter that you only use twice a year. So just take the batteries out and use your DMM to measure resistance or continuity or something like that. So they're really perfect for monitoring and adjusting and tuning circuits. Because for me, especially too, if I'm adjusting or aligning like an IF inside of a receiver, I'll much rather have an analog VOM monitoring the audio level, for example, coming out of the demodulator stage, because then as I'm tuning and tweaking the circuit, I'm just watching the meter go up and down and looking for a peak or I'm looking for a dip. It's a lot easier to watch, in my mind, a meter movement going up and down and watching that trend go up or down on the meter, rather than trying to figure out whether the numbers on my DMM are increasing or decreasing or peaking or not. So an analog VOM is really very valuable for doing that type of work and looking for trends and things as they're adjusting and moving back and forth. So that reason alone for me is enough reason to have one of these analog, VOMs. And I won't tell you how many just Simpson 260s I have, but probably more than I should, more than I can use at one time. So, and again, another thing I like about the VOMs, and I've said this a couple of times, is that they make you think. And that's good, especially when you're working around electronics. Thinking is good because it lets you make sure you're concentrating on what you're doing and you don't connect up to the wrong thing or short something out. So in my mind, making you think when working inside your electronics is a good thing. So with that, let's kind of switch our gears a little bit to handheld digital multimeters, or DMMs. Okay. Most of them are what are called 3.5 digit DMMs. Some are less, some are more. What does that mean? I've got 3 digits that go from 0 through 9, and then 1 digit that is usually just a 0 or a 1. That's generally what a 3.5 digit meter means. A 4.5 digit, might mean that meter goes, you have four digits, then one that goes 0 to 1. Sometimes you'll see a 3 3/4 digit, which means that the other digit goes from 0, 1, or 2 or something like that. But that's generally what that means. Now, some of them actually do have a kind of digital bar graph, okay, to kind of take the place of the analog meter movement. But I find that even though you might say, well, this kind of takes that function that I described in the analog meter, and now I have it here, I can watch this bar graph go up and down. Well, there's a limited number of segments in that bar graph. And also, if the meter auto ranges on you, then the bar graph bounces back and forth. So it may not be as useful as a true analog VOM. All right, so it doesn't completely take the place of the analog VOM, although it does give you some of that functionality. All right. Again, the vast majority are kind of auto ranging meters, and I think we'll talk a little bit more about that. Now, some of the meters, the DMMs, are geared specifically for like electrical and appliance work, kind of geared around, mains voltage levels and things like that. Others might be geared more towards industrial service work, and others more towards lower power electronics work. And a lot of that is really going to be governed by what types of measurement ranges you have and what other functionality you've got in that meter. So you just want to kind of keep an eye out when you're picking up a DMM that it's really appropriate for the type of work that you want to do. Think about the measurements you want to make, the devices you want to measure, and make sure that you've got the ranges covered and the functions covered for what you wanted that meter to do for you. So a little bit more about them. We talked a little bit about the loading of the analog multimeters being dependent upon the scale, right? Ohms per volt. So on the 1 volt scale, it might be 20 ohms per volt. At 10 volt, on the 10 volt scale, it's 200 k ohms per volt, etc. So the input resistance is a function of the scale. Most DMMs have a fixed constant input resistance, okay? And in most cases, it's 10 megohms. So whether I'm looking at a 1 volt scale or a 100 volt scale, it's still a 10 megohm input impedance. And also that's generally much, much higher than the analog VOMs are. So this is where you can get a little bit in trouble by using a digital multimeter to measure like the voltage coming out of your mains outlet. You might see a stray voltage there and think that, oh, I didn't cut the breaker off, but maybe you did, and you're just picking up stray voltage. Again, so this is where the lower input impedance might help you, and the higher input impedance of the DMM might lie to you. Most, again, are auto ranging, where you're only selecting the function. AC voltage, DC voltage, DC milliamps, etc., and it will automatically set the scale for you. All right. Many of them you can actually hit a range button to hold a range so that it doesn't auto range once you've selected it. But most will just auto range for you. Again, no thinking, just use it. All right. So I got to be careful with that. Okay, you set the mode and that's it. And you just have to use the correct jacks, typically the common jack, and then pick the right jack for the mode that you're measuring. Some of them will have separate high and low ranges, especially for current. That's very common to have a separate, in this case, in this meter over here, there's a separate jack when you're measuring 10 amps, but then use a different jack when you're measuring in the milliamps. So you do have to be a little bit careful about that, kind of similar to what we saw in the VOM. There are some that are not auto-ranging. This Uni-T example here, as you can see, has different ranges you can set. So it is not an auto-ranging meter. But I would say probably most are actually auto-ranging. Okay. You can, as I mentioned, you can turn the auto range off on these meters. So if you really do want to use the analog bar graph, it's best to set the range to the next range above what you expect to measure, so that now the bar graph won't bounce around if the voltage dips down below and we auto range to something else. Again, for doing those trend measurements using the bar graph, turning that auto range off can be handy. And also if you want to set specific loading, again, in most cases, the loading doesn't change, but some meters actually will change, particularly when it comes to measuring current. Because measuring voltage, it's typically 10 megohm input impedance. But when you measure current, the current is actually measured by these meters by sending the current through an internal shunt resistor and measuring the voltage across that. So the higher current measurement ranges uses a lower value shunt. Okay, so if you want to measure, a relatively low current, but you can't afford to drop much voltage across the meter, you might set a higher current range to minimize what we call the burden voltage. I'll talk a little bit more about that in a moment. Most will have a continuity beeper, which is handy to be sure you don't have broken wires and things like that. A few DMMs have a continuity beeper, but again, requires you to put batteries in them. Okay, so takes away one of the advantages of the VOM. So many DMMs have additional special functions, okay, which can be handy in many cases. They might be able to measure frequency. Now, they're not going to measure the RF frequency. They're typically going to be limited to, audio frequencies, or maybe up to 10 or 20 kilohertz or something like that, but generally not much higher than that. So don't expect it to be a frequency counter for RF. It won't do that. Many will also have min and max tracking. So if you're measuring a voltage and it's changing and moving up and down, the meter can remember the minimum and maximum values for you, so you don't have to kind of mentally track that. Some will also automatically measure a diode voltage. So you can test a diode very quickly, measure its diode voltage, maybe even do some matching if you're selecting diodes to put into a homebrew, diode ring mixer or something like that. You can use that diode voltage as a simple check to ensure that the diode is working. And what it does is it puts the constant current through the diode and measures the voltage drop across the diode. It's measuring at one point, and whether that one current point is where you're going to use the diode, is probably unlikely, but at least it's a constant way of doing measurements. Now, no two meters, in terms of different meter types, are going to use the same test current. So while a diode with one meter might read 0.7 volts, on another meter it might read 0.65 volts because it uses a different test current. So just be aware of that. The meters will actually measure capacitance. That's a handy thing. They're generally not going to measure really low value capacitors that you'd use in RF circuits, like a 10 or 20 picofarad capacitor. But measuring millifarads or microfarads generally is okay, and they're reasonably accurate and handy. Okay, some will have a temperature probe, so you can actually measure temperature with the meter. Okay, that could be handy as well. Some of them will measure the current gain of bipolar transistors, NPN or PNP transistors, as shown here. Again, it just puts a test current in and measure into the from base to emitter, measures collector current, and then gives you the result. Again, just a quick go test, and could be a quick way to do some rough matching if you want to do a differential pair of transistors, for example. So that can be handy. And also, some will offer the ability to do what's called a delta or relative measurements. So it's kind of like a tare measurement on a scale, where you want to zero out the weight of the container and then put your food in it and measure just the amount of food. The delta measurements allow you to do the same kind of a thing. Say I want to look and see how much does this voltage change when I do this. Well, you can put the probes on there before you do that thing, hit the delta or relative button, and then do the thing you're going to do to see how much the voltage changes. So it might be handy to look at how much of a voltage drop you get when you turn your transmitter on, for example. Okay. Now the bench DMMs are, again, kind of like the handheld DMMs, a bit on steroids. They're generally higher digits of resolution, from 5.5 to 8.5 digits of resolution. Okay, so much more precise measurements, higher resolution measurements. They're generally going to have higher accuracy. Instead of maybe a percent or two of accuracy, they might be down at 0.1 or 0.05% accuracy. They also allow for 4-wire measurements. They're often called Kelvin measurements, and really handy for measuring very low resistance. Because when you try to measure low resistance, the resistance of the leads themselves and the connection of those leads to the device you're measuring will all appear in the measurement. A 4-wire measurement allows you to remove the lead resistance and the connection resistance to get more accurate low resistance measurements. They'll generally also have logging, filtering, and averaging functions built into them as well as special functions in some cases, like this Keithley 2015 THD can measure total harmonic distortion. Okay, so other meters will have other functions and things like that. So you'll generally get some additional functionality with the bench style DMMs. Now, a couple of practical usage tips for both VOMs and DMMs. As I mentioned earlier, you've got to watch the loading, right? So in the case of using an analog VOM here, let's say I want to measure the voltage drop across this 1 megohm resistor. Well, if I'm on a low scale, if it's at 20,000 ohms per volt, let's say I was on the 10 volt scale, this looks like a 200 kilo ohm resistor. So simply connecting the meter up puts a 200 k ohm resistor in parallel with that 1 megohm resistor. Well, that's certainly going to change the operation of that circuit, okay? Because now the equivalent resistance of that combination is going to be something under 200 k ohms instead of 1 megohm. So the circuit operation is definitely going to change. So you do have to be cognizant of that. Again, on the VOM, that loading depends on the range you selected. On the DMM, it's typically 10 megohms. Okay, so in that case, if I put the DMM there, it would be very little change in the operation of the circuit. Now, the other thing to think about is when you're measuring current is what's called the burden voltage. As I mentioned, there's essentially when you measure current, you're inserting it in series with your circuit, but also in series with this that you don't see is a small value resistor, okay, what's called a shunt resistor. And the meter is measuring the voltage across that shunt resistor. And then from that, essentially determining what the current is. So the burden voltage is not zero, right? And it does depend on the range that you've selected. The higher current range, the lower the burden voltage. Okay, so the lower the resistance that's inside that meter. So if you're working on 12 volt circuits and drawing relatively little current, then 100 millivolts or 50 millivolts of burden voltage isn't going to bother you. But if you're working on something that operates on 1.5 volts, then maybe that burden voltage will bother you. So it's something to think about. Okay, and that's going to apply both to VOMs and DMMs. Okay. And again, the AC frequency range, again, typically audio frequencies only. You're not going to be looking at RF even when you're measuring voltage. Okay, not so both measuring the frequency on those meters that can do it. Even when you're just measuring voltage, you're typically 10 or 20 kilohertz is about the highest frequency that you can actually measure accurately. Now, some meters, particularly DMMs, will have something called true RMS measurements. Okay, a true RMS measurement gives you really the true, effectively DC or heating value of a waveform. Most meters that aren't true RMS will give you an accurate reading for sine waves only. So if your signal you're measuring is not a sine wave, if it's a square wave or a triangle wave or a complex waveform like an audio waveform, it'll still give you something close to the RMS value, but it might not be the true RMS value. For what you're doing, that may or may not matter, but it's something to think about. Okay, whereas a digital multimeter will say true RMS, and will actually give you the true RMS value of a waveform. If you're just trying to peak up the level of an audio signal or seeing when that audio signal increases by a certain amount or something like that, you don't necessarily care maybe about the absolute value being accurate. You're just interested primarily in the change or relative measurement. So in that case, whether it's a true RMS meter or not doesn't matter. But again, it's just something to think about. So in summary here a little bit, the analog VOM is kind of like your slide rule, right? Makes you think a little bit, where your digital multimeter is kind of like the calculator. You don't have to think about the operations. The analog VOM gives you a better feel for your measurements, just like a slide rule gives you a feel for the numbers. You kind of have to know a little bit about what to expect in order to use it properly. Where the DMM is kind of blind, you just punch in numbers and believe the numbers it says, no matter what, right? So the VOM is great for looking at trends, peaks, and dips. The meter itself, because it has some inertia to it, does some mechanical averaging. So if you have something that's varying relatively quickly, the mechanical averaging will help you get a reading. It might be really tricky to make a measurement like that on a digital multimeter with the digits bouncing around. Again, no batteries necessary except for resistance or potentially continuity measurements. Inexpensive, and they require thought, which is not a bad thing. Okay. The DMMs really give you much better accuracy and resolution than the analog meters do in general. And they're really simple to use. Most are auto ranging and have some additional functions. But just be careful because they can lull you into a sense of doing something quickly without thinking and maybe getting yourself into trouble. All right. So just some practical tips and why you might really want to have one of each of these in your shack. So with that, we'll switch gears a little bit, unless there are some specific questions that came up on Facebook or something like that we want to address.
Alan. No, I don't think we've had any. I've never heard of the burden current before. I thought that was interesting.
But, yeah, it's called the burden voltage, and you might think, well, an ammeter is just I just stick it in there and it measures current and doesn't do anything, but it does have an effect. It does a small voltage drop, and again, it's often called the burden voltage. So okay.
Anyway, thanks. Just a reminder to everybody at home now. I know you're intently watching and listening to Alan's talk on we just had multimeters, but if you have got any questions for him or points or maybe sharing some of the the equipment that you've had at home, then be ready to ask those during this part of the talk. So back to oscilloscopes. Thanks, Alan.
Alrighty. Okay, so let's switch gears a little bit and kind of go to a graphing voltmeter or an oscilloscope. I kind of think of it as a graphing voltmeter. Now, of course, we've got analog and digital scopes. The analog scopes these days are generally pretty inexpensive because almost exclusively they're all going to be used because there aren't that many new analog oscilloscopes being sold these days. So you're picking them up used at a rally or something like that or out of somebody's garage. Digital scopes can be expensive, okay? The analog scopes give you kind of an instant response, right? Because the waveform on the screen is driven directly by what you're putting into it. Digital scopes can sometimes be a little bit laggy because there's computations involved in the way the scope is working. Analog scopes are really, really good for looking at RF envelopes, like a station monitor, to look at what the RF envelope of your modulated signal looks like. Digital scopes can be a little tricky there because you get into issues with sample rate and aliasing and things like that we'll talk a little bit about, okay? But digital scopes can store and freeze waveforms, so you can look at them, analyze them, make some measurements. So single shot events, really good, right? Analog scopes generally don't have storage. There are some specialized storage analog scopes where the phosphor can actually store a waveform for a little while, but they're not that common. Digital scopes can make automatic measurements, frequency measurements, amplitude measurements, rise and fall time measurements, etc. Okay, generally analog scopes don't have automatic measurements. Some will have cursors that you can position on the screen to help you with some measurements. Otherwise, you're counting divisions on the gradical. Digital scopes will oftentimes have an auto set button to automatically set the scope up. Now, I call this the WIMP button, right? Because it gets you out of learning how to use the scope. If you rely on the auto set, you don't necessarily It may or may not optimally set the scope for what you want to measure, and you haven't learned anything about how to set up the scope properly, both for the vertical, horizontal, and trigger settings. So in my mind, you're wimping out a little bit, but I'm a nerdy engineer that focuses on getting the most out of equipment. So that's why I call it the wimp button. Other folks might call it the efficiency button because you could be up and running like that. Okay. So the analog scopes generally don't have an auto set button. And again, you have to think. Again, I'm a fan of thinking. So let's first talk about analog scopes and the cathode ray oscilloscope, where the display is a cathode ray tube where we're essentially sending an electron beam out to the CRT, which creates a spot of light by glowing the phosphor. And then the beam is moved horizontally and vertically by signals applied inside the scope to vertical and horizontal deflection plates. There is essentially an input that ultimately drives the vertical, and then usually a sweep generator that drives the horizontal. So we're essentially moving the beam across the screen, inside the scope itself at a speed that we determine by the horizontal settings. And then the input signal that you're measuring is driving the beam up or down. So we're effectively a graphing voltmeter is the way to think of an oscilloscope. So the scope itself will have, like the analog meters have a set of graticles. We've got a graticle on the scope. Again, major divisions, typically 10 by 10 on most scopes. In some cases, it might be 8 by 10. And then there's minor divisions. Oftentimes the minor divisions are 5 divisions per major division. So you just have to divide by 5, for example, to get that. And when you're setting up the scope, you might set up something like 1 volt per division. It's talking about the major divisions here. Okay, so if I had the vertical scale set to 1 volt per division, and my waveform moves from here to here, it moved 2 volts. Okay. So the display system, there are controls that are specific for the display, and they're generally intensity and focus and maybe a trace rotation, because the beam is deflected magnetically. The Earth's magnetic field can sometimes cause the trace to tilt to be, other than being perfectly horizontal when you don't have a signal input. And the trace rotation allows you to kind of compensate for that. If you move the scope around to a different spot on your bench, you might have to readjust that trace rotation because of the different static, magnetic field that is exposed to in that location. Intensity and focus are pretty self-explanatory. It might look like this on your scope. There's also something called a beam finder, and this is handy if you hooked up to your circuit and there's nothing displayed on the screen. Did the trace just simply get deflected off the screen because I'm measuring a very large voltage or I don't have something set right? The beam finder kind of collapses the deflection voltages enough so that if the display was off the screen, it'll bring it on and you can see if it was too high, too low, or off to the left or right. So it gives you a hint of where it went, okay, if it went off screen somewhere. So that's what that beam finder control is. Okay. So the vertical system, this is, again, we're going to take our signal coming in from whatever we're testing, and it goes through a number of different processes before being applied to the vertical deflection plates. Generally, there's an attenuator and a preamp and a delay line and an amplifier. So we'll talk about some of these controls. Now, you might say, well, each time I adjust like the volts per division, I'm adjusting the sensitivity of the scope. Why doesn't it just change the gain of the amplifier? Well, the reason for that is because making an amplifier that is uniform in terms of bandwidth and response with a very large gain range is difficult to do. So generally, the amplifier and preamp are set up with a fixed amount of gain, okay, the maximum that we'd ever need, and then we simply attenuate the signal coming in, okay, to establish the different scales so that the amplifiers can be optimized at one gain setting and optimized for bandwidth at that one setting. And we're just adjusting the level of the signal that hits the amplifier to set our different ranges. Okay, so that's our volts per division. We'll talk a little bit more about some of these other controls here in a moment, okay, or right now, okay. So the most common things you're going to adjust are the vertical scale and coupling controls. The scale is noted by typically volts per division, V per division over here, volts per division over here. Okay. On some scopes, you might see something like an actual vertical attenuator setting and a vertical gain control. These are generally uncalibrated service grade type scopes where you don't really have a fixed volts per division scale. You'd actually have to put a known signal in and adjust the knobs to get a deflection that you want. These days, there's almost no excuse for using or picking up one of these because you can get scopes with calibrated vertical scales pretty inexpensively these days. So if you see an inexpensive scope at a flea market or a rally or something like that that has these types of controls, look for something else. Okay. The AC and DC coupling does not refer to the type of signal that you're measuring. Unlike a multimeter, right? If I take a VOM or a DMM, I have to set AC or DC volts. The AC or DC coupling doesn't refer to that on a scope. What it refers to is how we're getting the signal from the input connector into the amplifier. AC coupling simply means we're going to put a capacitor in series with that, so we can remove the DC content on the waveform and concentrate on the wiggly parts. Okay, DC coupling means that I'm going to look at everything that's there. Okay, so here's an example. Let's say I'm looking at a little bit of ripple on top of a power supply. So maybe I've got my position so that if I connected to ground, my line would be down here. I connected up to a power supply and I see the power supply DC voltage and I see the ripple sitting on top of it. Now let's say I want to focus in on that ripple and see and really get a better measurement. Like I'm not even getting a full division here, so I can't get an accurate measurement. So you might say, well, okay, I'll go to a lower volts per division. I'll go from 0.5 to say 2.2 volts per division. What happens is now this whole waveform shoots off the top of the screen. So then you reach over and you grab the position knob and crank it down to bring the signal back down on the screen again. But eventually you run out of range. You can't bring it down anymore. By simply AC coupling, okay, we can remove the DC content of that, position ground right in the middle with AC coupling. Now I can increase or decrease my volts per division and get a much more sensitive reading and much more accurate reading by spreading that waveform out over more divisions by simply using AC coupling. So what's funny is that oftentimes you'll use AC coupling for measuring DC things like power supplies, but we'll use DC coupling when measuring AC signals through an amplifier, for example, because we might want to know, do the extremes of my signal start getting close to saturating a transistor or hitting the power supply rail? So by using DC coupling on those signal paths, you can kind of see where that signal is positioned with respect to how the circuit is biased. So again, oftentimes you're using their AC or DC coupling on the opposite type of waveform that you're looking at. So something to be aware of. The other thing to take note of is the input impedance to the scope. Most oscilloscope inputs are 1 megohm input impedance. Okay, we can see here 1 megohm. All right, we see down here, well, it's kind of hidden, 1 megohm. The other important thing is that there is some small amount of capacitance in parallel or shunt capacitance at these inputs, typically ranging from 10 or 12 picofarads to near 20 picofarads, okay, depending on the scope. So that it's just something to think about because you have to kind of, it might matter for what you're measuring. And then some of the higher speed scopes give you the option of selecting a 50 ohm termination if we're looking at high frequency or RF circuits. So, but typically all that information is all going to be printed on the front panel of the scope for you. So what about vertical modes, right? If you look at the mode switches, we've got all these different selections for vertical modes. What does that all mean? Obviously, we can select channel 1 or channel 2, or sometimes both on a 2-channel scope. Or if you have a 4-channel scope, you got additional channel 3 or 4. What Alt does is that if I have got both channels on, channel 1 and channel 2, what Alt does is that it will alternate between displaying the channel 1 trace for one sweep, then the channel 2 trace, then the channel 1 trace. It'll bounce back and forth between those two. Now, oftentimes your sweep speed is fast enough, but you can't see this, right? Because most of these scopes only have a single beam, a single electron beam, a single gun. So how do we display 2 channels? One way to do that is by alternating back and forth between them. Now, if you're looking at relatively slow signals that aren't changing very fast, you might be sending that sweep across at a slower rate. By sending that sweep across at a lower rate, you might actually see that alternating back and forth one waveform or another. In that case, you'd use this mode called chop. And what that does is it will alternate back and forth between channel 1 and channel 2 waveforms on the screen quickly, fast enough that you can't see it. Okay, so it truly looks like you have two beams moving across the screen slowly. Okay, so you use the chop mode when you're looking at multiple channels, but at relatively slow sweep speeds, maybe several milliseconds per division or less, or more, I should say. The add mode will, in this case, would add channel 1 and channel 2 and create a new trace that is the sum of those two. You say, well, why would I want to do that? Well, adding them is oftentimes not really very useful, but where it does become useful is when you add this invert function on one of the channels. So if I invert channel 2 and then add them up, what I'm effectively doing is measuring the difference between channel 1 and channel 2. And that can be really useful. Because if you think about using a DMM or a VOM, I've got two probes. I can put them anywhere in the circuit that I want and measure the voltage between those 2 points. So if I want to measure the voltage across this resistor or across the base and emitter of this transistor, I can just connect those 2 probes there and I'm fine. I can't do that with an oscilloscope. Because an oscilloscope, in most cases, is a single measurement probe with a ground lead. And notice I said a ground lead, an earth lead. All right, I can't just simply connect that anywhere in the circuit because that will connect that point of the circuit to ground. Okay, and if you're trying to measure across a component where neither end of that circuit is component is grounded, you can't just stick the probe across it. So what you can do is use 2 probes and then invert and add, and then the display will show you the difference measurement across that component. So the add and invert are often used together to measure the voltage across a component. So let's switch gears now to the horizontal system. That's controlling how fast the beam is moving left to right across the CRT. It's often called the sweep control or time-based control. On the digital scope, it's called horizontal scale because there's no sweep of a beam on the digital scope, so we'll get into in a moment. So let's look at some of the controls for the horizontal system. They're all kind of listed here, but let's kind of go through them. Well, actually, let's go through them up here because I think I'll talk about them later. But so the main control is the seconds per division, right? So how many seconds or milliseconds or microseconds or picoseconds is it going to take to move the beam from one major division? So that's the seconds per division control. There's a hold off control we'll talk about a little bit later for triggering. There's some trigger modes we're going to talk about here in a moment. Then obviously the position, how we're positioning the beam left to right. Oftentimes you're just going to set that so the beam goes completely across the display, but sometimes you might want to line up a feature of a waveform on a gradical so you can make a measurement. So the horizontal position allows you to do that. Okay. And generally that sweep across the display is driven by a trigger system of some sort to tell it when to start sweeping. So let's talk about horizontal sweep. Now, again, those old scopes that I mentioned that had the vertical attenuator and gain control, they're typically also going to be on scopes that have something called a recurrent sweep, where the sweep is driven internally by a sawtooth wave. We're going left to right across the screen, then we quickly return back to the left and go again across. And then the frequency of that is how fast we're moving the beam. And the controls on these recurrent sweep scopes, the giveaway is that you'll have a horizontal frequency selector as opposed to instead of a seconds per division control, you have a horizontal frequency control and then a vernier adjustment. That's kind of your key that this is a recurrent sweep scope and generally not quite as useful. The sweep runs continuously. It's not really based on a trigger. There is a sync control to try to lock that sweep to some feature on your waveform, but it's not really very effective. And again, they're usually uncalibrated because, again, I just have this vernier control from 0 to 100 over this range that I'm looking at, say 1K to 10K C, right? So uncalibrated. Again, older, simpler technology. And I would say generally, if you've got the choice of buying a recurrent sweep scope or a trigger sweep scopes, run away from the trigger sweep scopes or the recurrent sweep and get yourself a trigger sweep scope. A trigger sweep scope where you can set a calibrated volt or a sweep time per division. and the sweep starts in response to some trigger event. So it's very easy to stabilize the waveforms that you're measuring on the screen because they're always going to be synchronized to some characteristic of your waveform. And you also get this calibrated sweep time. So these are going to generally be the most powerful and flexible. And again, no real excuse to go with the recurrent sweep scopes. Something that I'll mention here that I neglected to mention on the vertical controls is that oftentimes there's a concentric vernier knob in the center of the multi-position switch for both the vertical scale and the horizontal sweep time. Generally, that control, when you turn it all the way clockwise and it clicks, you're in the calibrated position indicated by the scale. Most of these will have, if you rotate these counterclockwise away from the click, you will vary the frequency more linearly. It'll be uncalibrated. It won't be exactly what it says here in terms of milliseconds or microseconds per division anymore. But again, you might need that to position a waveform or make it look the way you want. But the calibrated position generally is by rotating that knob fully clockwise until it clicks, both for horizontal scale and the vertical scale controls that we talked about earlier. So let's talk about triggering. This is probably the most misunderstood or confusing things in a lot of people's minds. So why do we want to synchronize your trigger? And this allows us to stabilize a waveform on the screen. Because remember this, the waveform is painted over a certain period of time. And if each time we paint in the next trace going across, if we paint at a different location, it looks like the waveform's moving. Because we're really relying on that waveform to under multiple sweeps to land on top of each other, so we get a nice stable picture. So the trigger allows us to pick a spot on the waveform as our starting point, so that each time we hit that same spot on the waveform, we build up we overlay that portion of the trace on top of the previous trace. So now the fading of the phosphor is all kind of be reinforced each time that trace goes by. Again, the sync on the recurrent sweep scopes tries to injection lock the horizontal oscillator to your signal. And you got to sometimes play with the horizontal frequency and the sync amplitude, and it kind of barely works, and yuck. Yeah, you don't want to use it if you can help it. The triggered controls allow you to pick a spot to go, kick off the sweep, much more powerful. And is an example of what these trigger controls look like. They look confusing, but I would say in most cases, most people kind of followed what Tektronix did over the years, is that if you took all of the lever switches and you pushed them all up to the top position, then the scope's generally going to trigger for you. From there, you can kind of go adjust it, but putting all the switches to the top is generally a good default place to start whenever you've got kind of multiple positions here, like normal trigger, positive slope, auto triggering on an internal source, right? You're going to generally get a good stable trigger at that point to start with, okay? So let's talk about some of the trigger controls. Again, the trigger is what is going to kick off that horizontal sweep. So the trigger source is what are we going to look at to kick off that trigger. Internal means that I'm going to pick off a piece of a signal that's already in the scope, like my input signal, okay? That's most of the time that's what you're using. External trigger allows you to maybe provide another input to the scope to kick off the sweep. That's called external trigger. And a line trigger literally triggers off your line or mains voltage. This is handy if you're looking at power supply ripple, because power supply ripple is going to be a function of your 50 or 60 hertz line frequency. So you don't have to worry about adjusting the trigger, set it to line, and now your waveforms are going to be synchronized to the line frequency or mains frequency. The trigger mode, okay? There's auto mode, which is not an automatic setup of trigger. We'll talk about what auto mode is in a moment. Normal trigger is just, like I said, I get a trigger, I get a sweep. Okay, each time I trigger, I get a sweep. Single only happens once. You have to reset it to get another trigger or another sweep. Useful for single shot events, but with an analog scope, oftentimes you might have to be using a scope camera to capture that event so you can see it. And then some scopes actually have a TV trigger to trigger on the vertical or horizontal scans for analog CRTs in analog TVs. A lot more trigger types are available on digital scopes. Okay. And then trigger coupling, much like the coupling that we had for into the vertical section of the scope, AC or DC coupling, there's also typically separate coupling controls for trigger. Like you might want to reject the DC component and use AC coupling. You might want to actually trigger on a specific DC level. And then some of those are other features like a high frequency reject filter and things like that. So these are other controls that are available on your trigger. And all these are helping you to condition the signal that you're going to use to kick off the sweep so that you get the stable waveform starting at the point that you want. So a little bit more about auto trigger. Okay, again, it's not what you think it is. Here's the auto trigger on this 465 Tektron scope. It does not automatically set up the trigger settings for you. Okay, it's basically a usability aid to prevent a blank screen. Because under normal trigger, if the scope doesn't see a trigger that satisfies the level, that you've set up, you don't get a sweep. So the screen is blank. So you don't know, is my circuit dead? Is the scope dead? Is the signal off the screen? We don't know. Auto trigger works by waiting. The scope waits for a trigger. If a trigger event doesn't happen in, say, 50 or 100 milliseconds, then the scope just self-triggers to send a trace over anyway. Okay, so this allows you to see a live trace even if your trigger condition isn't satisfied. So this can be really helpful to let you see what's going on. So if you're probing something and your waveform is bouncing around and moving around, it looks like it's not stable. It could be that, okay, the signal's there, but your trigger settings aren't sufficient to find that particular trigger event on your waveform. You might need to adjust it. And then the waveform will get stable when you properly set up your trigger event. So if you were just using normal trigger under that condition, you wouldn't see anything at all. So that's why the auto trigger is really a visibility or usability aid. But then once you start getting trigger events, the scope is actually seeing them, then it will essentially trigger on your signal and not self-trigger. The self-trigger is more of like a timeout, okay, to see that. So if you're looking at very infrequent events that don't happen very often, then you might need to use normal trigger instead of leaving it in auto. Okay, because the auto trigger might send a trace over even while you're still waiting for a real trigger event to happen. So again, if your trace is rolling or unsynchronized, then it's likely you're seeing auto triggered sweeps and your trigger settings aren't being satisfied by your signal. So basic controls for trigger are level and slope. Oftentimes, especially the analog scopes, you're triggering on an edge when the waveform goes through a trigger level. So in this case, the trigger level is adjusted positive. I'm going above the center line. So in this case, I'm going to trigger on a positive slope when the signal goes above or goes from below to above that level. Okay, if I adjust the level down, okay, then, or in this case, I adjust the slope from positive to negative. Now I'm looking for when the signal is dropping down through that particular level. Okay, if I adjust the level, okay, we're adjusting now. See, my starting point is down now below my center gradical. Okay, so the level control is essentially a threshold. The slope control tells me which direction I'm going to pass through that threshold to send a trigger off. So that's what the threshold are. The slope is essentially a rising or falling edge through that threshold voltage. And 99% of the time, this is all you're adjusting, is essentially a trigger level and a trigger slope, rising or falling. Okay, there are many more specialized trigger types and adjustments, but this is what you're going to probably use 99% of the time. So let's kind of talk a little bit about how digital scopes are different, right? The analog scopes, we're moving a beam vertically based on our signal and horizontally based on our horizontal controls. The digital scope is actually just a high-speed sampler. This is kind of what it looks like, very simplified. Input front end going into an analog to digital converter. From that point, I've got sampled voltages, okay, snapshots of the voltages over time that are going to then be processed, and then a trigger is going to get involved in there to figure out what I'm going to stick into memory. And then we go off and play with all those numbers and display on a computer screen effectively. The big difference is that the trigger now helps us to decide what gets put into memory. And what that also means is I can actually see pre-trigger and post-trigger data, because I might say I want to put the trigger position at a certain point in the display, rather than, because I'm not kicking off a sweep, I'm just identifying a feature that I want included in my captured waveform display. And that feature could be positioned in places other than the beginning. So same basic front end as an analog scope. The input is sampled, so we're creating voltage samples at some sample rate. So there's an interval between those snapshots of voltage that I take, which is essentially 1 over the sample rate. If I sample at 200 megasamples per second, okay, or I sample at 100 megasamples per second, 1 over that is the interval, time interval between the samples. And then all of the processing is done on this sampled waveform that we're sticking into memory. So let's talk a little bit about sample rate and memory depth. Okay, so sample rate, memory depth, and horizontal scale are all related, right? Horizontal scale is going to determine, again, number of microseconds or milliseconds per division. If I have 10 divisions, it essentially sets my acquisition time, right? My acquisition length. And then my sample rate sets how many samples or pictures I'm taking of the waveform over time across that acquisition time. Obviously, the faster the sample rate, the more samples I'm going to have in a given acquisition time. So we have this relationship, the amount of memory that's needed to store the waveform is equal to the sample rate multiplied by the acquisition length. Okay, and then you can rearrange that formula in 3 different ways to figure out what you need for acquisition length or sample rate. The scope will generally take care of all this for you. It will tell you what it's doing, but you have to be smart enough to see, hey, is my sample rate fast enough for what I'm trying to measure, right? And you often will have adjustments for the memory that you can use. So let's say I'm trying to measure an RF signal over a certain time period, and the scope decided that, well, for a 1,000 point memory depth, I'm going to use a sample rate of 2 megasample per second. Well, if I'm trying to measure a 7 megahertz signal, that's not enough. But I need to measure over that time period. So I might need to increase the memory so that my sample rate gets high enough so that it's oversampling my RF signal sufficiently. Okay. So oftentimes, though, we're measuring low frequency signals, the sample rate is way more than we need. Okay. So we might be sampling at, a gigasample per second. I may not need that if I'm looking at an audio signal. So how do all those snapshots or pictures get displayed? Okay. Oftentimes, the scope is going to always sample at some fixed sample rate. And we might take all of those samples that go into a displayed point and maybe create some kind of a, intensity graded pixel, okay, for that particular thing, or maybe a whole column of pixels at that point in the waveform to try to emulate what an analog scope would give you. Okay, so this display processing will vary a little bit depending on the scope that you're using. Now, some scopes don't do the intensity grading. It'll just take all of these points that got in that display interval and put them all here. And that's why sometimes people will say, well, my digital scope is a lot noisier than my analog scope because it's treating every one of these samples with an equal weight and lighting it up just as bright. So the analog scope is still seeing all of that, but the analog scope might not show you as brightly on an analog CRT a momentary blip because it's only occurring infrequently and doesn't light up the phosphor enough for you to see it. Okay, so the truth is that digital scopes aren't necessarily noisier than analog scopes. They just appear to be because of the way they're handling samples. So some of the digital scope advantages. Well, you can do single shot captures and zoom in on a portion of a waveform to see what a glitch looks like. Again, the single shot capture capability. You can get pre-trigger information, right? I can set my trigger point in the middle of my waveform, like right here, and see what happened before the trigger as well as after. Many, many different trigger types. Okay, in addition to just simple edge triggers like we talked about, there's lots of other trigger conditions to trigger on a particular pulse width or a particular, rise or fall time or something. Lots of different options. And you also get the automatic measurements, peak to peak measurements, period measurements, frequency measurements, rise and fall time, all these things rather than counting radicals and figuring out, how fast or how large a signal is. The automatic measurements can really help you out, maybe even a frequency counter, for example. So lots of features on digital scopes. Again, they're going to depend on, a lot of this will depend on the scope that you buy and how much money you spend. You can oftentimes do waveform math. Okay. In the case over here, I was actually looking at the reverse recovery time of a diode, and I was measuring, this was actually reverse recovery of a bipolar transistor. So in this case, I was looking at collector voltage, voltage applied to the base, and voltage appearing at the emitter. And then this was, I'm trying to remember what I did here, but I was actually using math here to compute and display base current. So this is probably now, actually, if I think about it, it was voltage across a series resistor in series with the base. So one on one side, one on the other, and then using math to take this guy minus that guy divided by the resistor value to actually give me current. Okay, so waveform math can be really handy. Sometimes you can do advanced features like a Fourier transform to look at spectral content, like a spectrum analyzer of a particular waveform. And lots of other advanced processing features are available on digital scopes. So what are some of the disadvantages, right? They all sound great so far. They're generally smaller, they're lighter weight, that kind of a thing. But again, they can appear noisy for the reasons that I mentioned, because they sometimes, if they don't have intensity grading, they'll show you every sample at every that was captured at a given point in time, display interval, if you will. Whereas an analog scope those infrequent things are going to be dimmer, so you don't see them. This is probably the biggest disadvantage, is that you can alias signals when the sample rate is too low or below Nyquist. Let's say our red signal here is our actual signal. Let's say the green are our actual sample points. And we can see that if we don't sample fast enough to capture this red signal, let's say my sample rate is too low, what happens if we connect the dots of all these samples that are happening? You connect those dots and you're getting a lower frequency. It's effectively a mixing process, right? But what we're getting is essentially an alias of our real waveform. I call this the wagon wheel effect. If you ever watch the old Western movies from the old wagons being pulled by horses, sometimes it looks like the wagon wheels are turning backwards in the opposite direction. And it's all because the camera's frame rate conspired with the wheel's rotational rate to take pictures of the wheel when it was in a position where it looked like it was going backwards. That's essentially aliasing. The same thing can happen if we don't sample a waveform fast enough. And this is probably the biggest Achilles heel of most digital scopes. So if you are looking at a waveform that appears like it's rolling at some low frequency and it's just rolling and noisy back and forth, oftentimes that's what the aliased waveform looks like. And what you might need to do is increase the amount of memory being used, which will then in turn make the sample rate go higher and maybe get to the point where you're avoiding doing the aliasing. Update rate on digital scopes can be slow, particularly if you dial in more memory. So these things can lead to problems when trying to look at RF signals. If you're trying to use a digital scope to look at the RF envelope of the signal, you might want to have a slower horizontal scale so that you can see maybe the audio content of your single sideband envelope, but that's going to force the sample rate to be lower, and you might undersample the RF carrier and you get some ugly looking waveforms. So then you say, okay, I need to use more memory, okay, to fix that problem, but then the scope gets too sluggish to watch the envelope. So again, analog scopes are better for looking at RF envelopes. Again, they can be pricey because they are still available, but even there are inexpensive digital scopes from folks like Regal and Siglent that are, $300, which isn't that expensive comparatively speaking. So, and generally, if you use a scope for doing XY mode, where you have an input signal that drives the X position and an input signal that drives the Y position, analog scopes are much, much better at XY mode than digital scopes are. So we'll switch gears a little bit again here to talk about probes. Let me take a quick sip. So probes are what we use to get our signal into the scope. So we also want to use them to minimize the amount of loading that we're going to be presenting. We talked about loading with multimeters. The same thing happens with scopes. The probe types, the most common are passive probes that are 1x or 10x attenuating probes, 10x being the most common. We'll talk about that why in a moment. There are also many other probe types available. There's active probes, differential probes, current probes, high voltage probes, and others. So let's talk about 1x and 10x passive probes. So a 1x probe is a direct connection to the scope input. It's really nothing more than an extension of the coaxial connection of the scope itself. They're generally only good for low frequencies, okay, mainly because, and lower impedance circuits, because they can have some pretty excessive capacitive loading. The scope input itself, again, 10 to 20 picofarads. The 1x probes will add to that. Typically, you're going to have about 100 picofarads of effective capacitance at the probe tip. Now, if you're looking at an audio circuit or in a low impedance circuit, it may not matter. But if you're trying to look at something RF or poking around in the IF of a receiver, 100 picofarads to ground might be a detrimental thing, right? So that's why 1x probes often aren't used. 10x probes basically isolate the probe and cable capacitance with a 9 megohm resistor right at the probe tip. So what that does, that 100 picofarad of capacitance going back towards the scope is on the other side of a 9 megohm resistor. So the circuit isn't really going to see it. Okay. So along with the scope input, though, it attenuates the signal by a factor of 10. So that's the trade-off. You get much lighter loading on your circuit, but your input signal is smaller. So but just the scope will just have to account for that. And the scope, you can actually set a scale for that. So to tell it you're using a 10x probe. So again, the good thing is it reduces the effect of capacitive loading. The bad thing is it needs compensation. So we'll talk about this next. So what do we mean by compensation? So here's a simple model of, here's my probe, here's my 9 megohm resistor, here's my ground clip. Then I've got my coax, okay, which is right in here. This could be, a meter long or 3 feet long, for example. And now I've got the scope input, which is my 1 megohm input resistor and the scope input capacitance. All right. And you've got the capacitance of the cable as well. So again, generally from this point back, you're looking at about 100 picofarads, right? But this series resistor forms effectively a low pass filter with the input capacitance of the scope, right? So at very, very low frequencies, the 10x voltage divider is just this 9 megohm resistor and this 1 megohm resistor. But as soon as you get up above just a couple of kilohertz, the reactance of this capacitor starts getting smaller than 1 megohm. And you effectively now have an RC low pass filter, right? So what the scope is designed to do, the scope has an additional capacitor placed in parallel with the 9 megohm resistor. So that now as the frequency goes up, instead of, at low frequencies, the voltage division is handled by these guys. As the frequency goes up, the capacitive ratio of this capacitor and this capacitor to basically make a capacitive voltage divider that maintains 10x, right? So that allows you to essentially get a good high frequency 10x attenuation and low frequency 10x attenuation. The problem is that not all scopes have the same input capacitance. So for the probes have to be adjustable so that you can adjust this capacitor to be an appropriate 10-to-1 ratio with the input capacitor, okay? And this is why if you look at a scope, there's usually a probe calibration or probe compensation signal on the panel of the scope, and it's generally a 1 kilohertz square wave, all right? The reason we do that, 1 kilohertz is a low enough frequency that the resistive divider takes care of us. But with the fast edges, there's a lot of high frequency content, all right? So that allows you to adjust the compensation capacitor. And as you adjust that, you might adjust from being undercompensated, where that input capacitor is too small and you're seeing the RC filter effect of this resistor and this capacitance, or you're overcompensated, where this capacitor is now too big and you're coupling too much high frequency energy too soon, and you overshoot the rise and fall time. So by adjusting the compensation capacitor in the probe, between this condition and this condition to get to this point, you've now flattened the frequency response of that probe. So if you haven't done so already, take the probes that you use with your scope, go dig up the little screwdriver that came with the probe and adjust and compensate your probes properly so you can get accurate measurements above a couple of kilohertz. So most scopes will have a compensation signal on the front panel to do that. So another thing, I mentioned this earlier, probe ground. It's a ground lead. It's connected to ground. So wherever I connect this probe connects it to earth or ground as far as the scope's concerned and as far as your circuit's concerned. So you can't just clip this around any component. This is essentially connected to ground. The other thing to think about when you're talking about higher frequencies is this wire looks like a small inductor. You want to keep it short when you're looking at RF signals, right? Because that inductor in series with essentially the probe capacitance can create a tank circuit, okay? So here's an example, probing a high-speed edge on an analog scope with a 5-inch ground lead. I can see my high-speed edge and I'm getting some ringing due to that L and the input capacitance. If I probe that same exact signal using this type of a ground clip, I minimize that ringing and that distortion, okay? So it's something to think about. You also want to be careful about the loop area when you're doing this. If you can kind of maybe, if you can't avoid using a ground lead like this, at least if you can, coil it around the probe body to minimize the loop area, okay, to minimize the inductance. So another thing with scopes, analog scopes in particular, is something called XY mode. This is where typically like channel 1 drives the horizontal position of the beam instead of the horizontal controls, and then channel 2 drives the vertical position. This is what it looks like when you take, say, Pink Floyd out of your stereo and put the left on channel 1 and the right on channel 2. You can actually see the stereo separation, right? If it was monophonic, I have a horizontal line here, right, like an Etch-a-Sketch, okay? But because I have different signals on left and right, I create this kind of wiggly thing, okay? Just more fun than anything else, but there's some useful things we can do with it. In the old days, before we had frequency counters that were readily available and things like that, you can actually measure and compare frequencies in phase. Whereas if I've got a 2-to-1 ratio between the X and Y frequencies, I'll get like a figure 8 pattern that'll kind of rotate around, 3-to-1, 4-to-1, etc. Yeah, maybe not so useful, but just kind of fun to look at. But you can do some interesting things like a simple curve tracer, like taking a little filament transformer, okay, with a couple of resistors and a couple of test probes going to a device that you're measuring and go into the horizontal and vertical input. And you can get various waveforms for resistors, opens, shorts, capacitors, diodes, things like that. Real simple go, no-go type tests. There's a famous piece of equipment called a Huntron tracker that was often used for this. And some scopes actually have this little curve tracer thing called a component tester built in, and that's basically what it does. More complicated, complex example using XY mode is, let's say I have a function generator where I can sweep an output frequency going into a receiver, for example. Let's say I'm sweeping that, and I have a ramp output whose voltage is proportional to the frequency that I'm sweeping through. I can bring that into X and Y, okay, and then plot out the frequency response of an IF filter, for example. Use this to kind of align a radio. Okay, so more complicated example, but it's a way you can use XY in your scope, okay, amaze your family and friends. So the big question always is analog or digital? In many cases, digital is better, right? Automatic measurements, they're smaller, they're lighter, you acquire into memory, all the things that we talked about. But for an RF envelope measurement, like a station monitor thing, analog is generally better. You don't have to worry about sample rate and memory and aliasing and all of those kinds of things. So at slow sweep speeds to see audio, RF can get undersampled on an analog scope. So you get that aliasing problem. Increase the memory to avoid that, and the update rate suffers, right? An analog scope doesn't have that problem. Plus, an analog scope naturally gives you that intensity grading. Here's a quick picture of a single sideband RF envelope on an analog scope. And if this digital scope doesn't have intensity grading, it doesn't really give you as much of an intuitive feel for what's going on with your waveform as an analog scope does. So maybe kind of like the meters, you want one of each. So let's talk about a couple of ways you can use a scope in a shack here. And I was just looking at the clock here. I've got 20 minutes till my cutoff here. So but we'll go through this quickly and we'll get to some questions. Transmit signal monitor, coax analyzer, like doing a TDR, circuit troubleshooting, rig and equipment debug and repair, and measuring things like unknown components. I've got videos on all of these topics, so you can use, typically an RF sampler or a demodulator to actually get the RF envelope on your scope to go look at what your RF envelope looks like. So you want to look for things like flat topping, you look at modulation depth, things like that. Very easy to go do. Okay. You do a simple time domain reflectometry. You can have a fast edge going into your transmission line and look at the reflection coming back. From that, you can calculate a distance to a fault or distance to figure out the length of the coax. I converted this to metric. I wasn't sure if metric or English is what or imperial units would be the most common. Free space velocity for the signal is 30 centimeters per nanosecond or so. In typical coax, with a velocity factor of 0.66, that will translate down to just under 20 centimeters per nanosecond. And you can figure out the length of a hunk of cable in meters by basically computing this function out, which simplifies down to taking that delta t from the reflection coming back, multiplying by 0.099. That'll give you a very close length to coax if the velocity factor is 0.66. You can use some simple circuits to measure RC time constants and LC ringing for tank circuits to measure unknown inductors and capacitors. Again, I've got videos on all of these topics. This is just to kind of give you an idea that these kinds of things are out there. So let's leave this last 15 minutes or so for questions and anything that you've got. So I appreciate you guys staying awake.
Oh no, not at all, Alan. It's I've been a professional engineer since I trained with Pi, which is Philips, in the 70s, and I've learned a lot tonight, and I'm sure everybody at home has as well. I bet there's a lot of people who've bought an oscilloscope because, as you say, I've seen them quite cheaply at rallies, especially the analog ones, but really not sure how to use them. And you've gone over an awful lot of detail there in a very short time. We haven't got many questions, but I'm going to keep them short because I don't want you to run right up to your meeting as well. It's not fair. Okay. Just worth telling everybody at home as well that you do work for Tektronix professionally, so you know what you're talking about. And
yeah, I'm a field application engineer for Tektronix. I've been for the last 15 years.
Lovely. Yes, thanks. So let's say I think we had one or 2 points here, questions. Yeah, here we go. Paul Burgess, a comment more, I suppose. G3VPT says, I've found a digital multimeter can give an incorrect reading if there's a lot of RF about. An analog one can be more reliable and realistic, he says.
Yeah, and that's primarily due to two things. One is that very high input impedance of those digital multimeters means that those wires can act like antennas, and very small induced currents can create a voltage because it's looking into a very high impedance. Plus, just the circuitry itself could be subject to RF fields. So those are generally the reasons why, but that's absolutely true.
Yeah, and we actually haven't got any real other questions or comments. I think people have literally been so intent about it. I was fascinated to hear what you said about analog versus digital, because like you, I love an analog meter as well as a digital. I also find that it's easier if you're doing lots of testing. An analog meter, the sort of meter in the corner of your eye, you can see whether it's moving or fluttering without having to keep looking at it. If you're fault finding or something like that, I expect you feel the same. But a scope, and I don't mind telling you, I did buy, because Tektronix makes some quite affordable digital scopes now, don't they? Sort of over here, £300-400, sort of, I guess maybe more designed for education, but they are quite affordable. And I find that now I don't use an analog scope much. I had a Hameg one. I don't know if you know Hameg over there. I don't know if they've made it over to the States. And that was a sort of a hybrid. It had digital readings on it as well, so you could do some readings. It certainly told you what your settings were as well, which was useful. But I find the digital mainly is better. What about you in your ham world when you're not professional doing this? What do you find you use
down
most?
on my bench where I do all my videos and things like that, the main scope on my bench is a digital scope, but I do have the analog scopes there. And sometimes, like I said, there are those situations, especially if I'm looking at RF signals. I want to look at envelopes and those kind of things where I know a digital scope, I'm going to run into some of the limitations. I'll do that. I'll still go back to the analog scopes. You'll see that in my videos too. Especially more of the later videos, I'm always using the digital scopes because I'm taking advantage of all the features and advantages of storing waveforms, and waveforms are different colors on different channels and all these things, where on an analog scope, everything's the same color, but there are those situations where, hey, we got along with, analog scopes for 50 years before there were digital scopes. So there's certainly a lot you can do with the analog scopes. There's, it's only when we want to start taking advantage of the later technology where the digitals are better. But that one case of looking at, I want to look at the RF envelope of my transmitter sitting behind me here. The scope that I have there is actually that old Kenwood SM220, which is really an analog scope, right? And that's better at showing me what the RF envelope of my RF output is than any of the digital scopes that I have, and even the ones that I use professionally.
And I guess if we think about the raw physics of this and the basic waveform, a scope is really raw, isn't it? You've just got X plates and Y plates, and it is showing you what's there. There's nothing added, nothing taken away, essentially.
Right, exactly. Yeah, exactly. In fact, even that I keep the wrong finger.
Right.
Even that guy right there, when you use it as a station monitor, it doesn't use any vertical controls in the scope. The coax goes in and comes out the back, and all we're doing is capacitively coupling the RF directly to the deflection plates of the scope with maybe an attenuator. That's it.
And it is just, it doesn't kid you. But then I love the fact that you can, particularly I think, a storage oscilloscope in analog was just so ridiculously expensive with the long phosphor. It was just never the thing. I think that's my favorite feature effectively about digital scopes, is that it's built in storage. You can just press a button, do a one shot, you can store one image, and it's there for you to have a good look at and later on, that you just couldn't do with an analog scope. Must give you a good figure, because I don't want to run it too close to your other meeting. It's not fair to you. But Mike G4DYC has said, Alan, I feel happier now using my Kenwood SM230 for checking my RF. So you'll know about that.
Very good. Yeah, the 230 is the successor to the 220 that I've got here. So
I've got one question for you, Alan. It's a difficult one. I guess it always relates to price as well, and that is the frequency. When you see a scope, I'm sure a lot of people watching this now are thinking, well, maybe I could buy an oscilloscope. And that frequency you quoted, normally, they used to be sort of 20 meg, didn't it? Started at 20. Now it tends to be 40 or 60 meg and then upwards. What do you need to buy if you want to look at not just the analog waveform, but if you want to look at, say, the RF waveform? Is it still sort of twice the frequency roughly that you need to have as a bandwidth, or what?
It's a great question. When you talked about the analog scopes, the general rule of thumb was if you needed to make accurate amplitude measurements, then the scope bandwidth had to be 5 times the RF frequency, because the roll-off of the scope is kind of a single pole roll-off. And what we're specifying when we say it's a 40 megahertz scope, that means that we're 3 dB down at 40 megahertz. So in order to have less than a 2% error, you got to be 5 times less than that. Okay.
Yes.
That with the digital scopes, rules change a little bit for 2 reasons. One is oftentimes there's digital signal processing involved, and the roll-off is generally steeper than that single pole roll-off. So sometimes you can get away with less than 5 times your signal. But the other thing to think about is it's still specifying a 3 dB bandwidth, but it might be a sharper roll-off. So you might have a more accurate frequency measurement closer to that edge. But the other thing to think about is sample rate, right? Because you have to ensure that you're oversampling your highest frequency by at least 2.5 times.
Yeah.
So if you're looking at 100 megahertz signal, you want at least a 250 megasample per second sample rate. Okay. So you have to think about that. The other thing to remember, though, is if you don't really care about accurate amplitude measurements, you just want to look relative, what does my waveform look like? You can generally put a signal in that's greater than the bandwidth of your scope. Because that little Kenwood SM220 is a 10 megahertz scope. I can look at the RF envelope of a 6-meter signal. Okay.
Right. Okay. Yeah.
I don't care about the amplitude being accurate. I can just see it, right? I don't care that its amplitude is depressed. You can get away with that a lot more on analog scopes than you can with digital, because in digital scopes, you might run into the sample rate aliasing problem before you run into a roll-off problem. So
if you're just looking at rough shape and waveform and things, an analog may be more flexible.
Yeah, and the other thing, if you're looking at other things like digital circuits, clocks, maybe microcontrollers and things like that, it's not necessarily just the clock rate you got to think about. You got to think about the rise and fall time.
Yeah.
Okay, because the rise and fall time, the faster they are, the more higher frequency content that's there. You might have a 10 megahertz clock, but if it has 1 nanosecond edges, there's frequency content in there above a gigahertz. So,
Alan, it's been a journey. I mean, in an hour and a half, something just over that, to take us through not just multimeters but scopes. It's a very heavy subject, really, for a lot of people. But as I said, I think there's a lot of people who've bought a scope or maybe thinking about a scope, just wouldn't have a clue how to start. And you've given us a really good overview of the advantages, disadvantages of both, and what to buy. We're really grateful for you joining us tonight. Thank you very much. I want to let you go now to have a little bit of a break before your meeting in a moment.
Yep.
But thank you ever so much. And I believe you've got a little talk there on nano VNAs, which maybe I can persuade you to come back and give to the club sometime next year if you're able to.
Yeah, I've got a couple of others prepared too, so we can decide what's going to be best, and or if we have enough notice, do something new.
Well,
so we'll figure it all out.
That would be lovely. Alan, thank you ever so much for joining us tonight and for giving us your wisdom and your knowledge about scopes and multimeters.
Thank you very much, David. Thanks, everybody, and we'll see you again. Take care.
Brilliant. Thank you very much, Alan.
Bye.
There we are. That's Alan Wolke, W2AEW, coming live from the States there. And that about concludes this week's NARC Live. I would just like to mention, by the way, we did see a message come up on there, not really for Alan, but a mention that John G8VPE is celebrating his birthday tomorrow. So happy birthday from us to him. Just to quickly tell you about what's happening on the club next week again. We've got the Monday Night Net with Tim, M1 MIT at 7:30, at 8:30, the 80 meter CW net on 3.543 megahertz. Next Wednesday here, the 27th of October, Joe Chester, M1 MWD. Please don't miss it. He's a character. Let's just say that. And as well as it will be fun, it's all about having fun with a small station, but you'll learn quite a lot as well. He's even set us a little challenge. So if I can get myself on a particular radio, apparently, we don't know any more than that, he's going to show it. So it will be a lot of fun. I hope you'll join us then. Do keep telling us as well about your news, sending us your pictures and things like that. Send it to this address, radio@dcpmicro.com. So if you can get it to us as soon as possible, and certainly by 3 o'clock next week, including those entries as well to the mystery competition. We haven't had any thoughts tonight on that. So what on earth is this? Don't forget to let us know. But until next week on NARC Live, from Tammy M0TC.
Goodbye.
And from me, David G7URP. Good to see you. Take care. Bye-bye.